Yes, good morning, all of you. Can you see the screen? The screen is visible. Yes, one of you can confirm me whether the screen is visible to all or no. Okay. So last class we discussed about the derivation of Euler's equation. Now today we'll discuss the extension of that Euler's equation and Bernoullis equation, and we'll try to solve some problems with Bernoullis equation. And in the break time, I'll take one more example which one student has asked a doubt to solve one more example on your viscosity, okay, in the properties of fluid on viscosity. That problem I'll take in the break. So until that, we'll go with the regular classes. So I hope until the this derivation I have repeated twice uh, how to consider this sketch in the flow with forces which are acting on the fluid that we consider with weight also. So weight is also one of the force which is acting on the different bodies. So taking that into consideration, we derived in this form, that is force equal to pressure force plus gravitational force we have taken. So after analyzing all these equations, we have written this mass into acceleration. So mass into acceleration we have considered rho into volume. So that volume is area dA and length of that volume is ds. So that becomes the mass of the given fluid element, and into acceleration is the velocity into change of velocity with respect to distance. So there we, after taking the equation, after simplification, we have taken velocity into dv by ds. This we have taken. On other side, pressure force. So pressure force, effectively we are getting minus dp dA. This is the extra force what is opposing the flow. And gravitational force is also acting downside, that we consider minus rho g dA dz is the gravitational force acting downside. So that gravitational force, after consideration, we have written like rho into g into this dA dz. Now coming to the simplification of this equation, you can, all of you can see dA is a common term. See here, in three terms we have dA as a common term, and also we can consider some other terms. So by dividing this dA, okay, and rho dA, okay, so once you divide by rho dA throughout this fifth equation, if you see, what we can get is, okay, one side if I consider, I can get dP by rho. So as it is divided by rho dA, first term, if you see, dA get cancelled, we left with minus dP by rho. So that is written here. Okay. Next term is minus rho g dA dz. Once we divide by rho into dA, just a minute. I think here rho g dA dz and rho dA dz. So that they have considered as a sum here after consideration common terms. And in the other side, if you see, v into dv by ds. Okay, so considering all these terms and dividing the common terms, we can get it as v dv into g dz. So here if you see the g dz, again it is divided by rho into dA. If you divide by rho into dA, I will get g into dz. Okay. Next is in other side, rho dA ds if you see, and if I divide by rho dA, what I'll get? I'll get ds. So this ds into v into dv by ds can be cancelled. So after cancelling this ds, we left with v into dv, and here we left with nothing because rho dA is cancelled, ds is also cancelled. So this term to cancel, we have divided fifth term by rho into dA. Okay, and after changing the signs, we left with dp by rho plus v dv plus G dz. If you take all these negative terms to the right hand side, I can write these negative into positive sense. So V dV plus dP by rho plus G dz equal to constant. This step is clear. Fifth to sixth equation. Or you can write a note there, dividing the fifth equation by rho dA as a common term. If you divide by rho dA and cancelling this ds term here, ds divided by ds, if you cancel, we left with dP by rho plus V dV plus G into dz equal to constant. So this equation with derivative of pressure or derivative of velocity or the potential of the datum line z or the height or the elevation, some problems they can consider it as elevation, vertical height. So if these dp, dv, dz values are there, that equation we are calling it as Euler's equation. And here the speciality of the Euler's equation, or to remember this equation, one can remember that the sum of the pressure head, that is dP by rho, pressure head, kinetic head, that is velocity, okay, plus potential head, or can call it as potential energy also sometimes. So that potential energy is because of the difference in the level or the difference in the head, how the flow is going to take place. So these force, if you add, it will be a constant value. So at any given point in a flow, either it may be entry side or a center point of the flow, or at the outlet side, if you consider any point, and if you take the sum of pressure head, velocity head, and the kinetic head, potential, kinetic, and the pressure head, or you can consider pressure, energy, velocity, and the gravitational force, whatever is acting. If you take the sum of all these three factors, it will be a constant, or it will be one number for any point of the flow. So this is shown by the Euler's. Next, same term. I hope this point is clear to all. The step what I have converted from fifth equation to sixth equation. All of you understood the Euler's equation? Next is to derive the Bernoullis equation. So anytime in the question paper or the question may be asked like derive the equation for Bernoullis equation, then what you have to do is you have to start from again the same thing, Euler's equation only, considering these two sketches and considering any one flow in that one element you can consider. And after deriving the Euler's equation, just you have to do is one step integration you have to do for the Euler's equation. This is nothing but also the derivation of Euler's equation as well as Bernoullis equation. So here next step is integrating this Euler's equation and converting the equation to the other form. So that is done by Bernoullis. And this equation will give us very important conclusion that sum of all these factors, how it will be constant. Then the same Bernoullis equation we are considering for the different types of examples also. So see the derivation. Okay, after derivation or the derived component of this Euler's equation, now we are going to integrate it. So integration of, see here, integration with respect to what we have to do now. The first term we can integrate with pressure. Next term we can integrate with velocity dV. Next term we can integrate with the elevation, that is z, or the potential head, that we can derive or take the integration. So considering that, one can assume that density for a given liquid throughout the flow, it is remaining constant. Okay, that value we have taken outside, 1 by rho, integration of dP, again V into, or you can take V inside also, integration of V dV plus integration of dz, G can be taken outside. So once we integrate all these derivative components, what we'll get is capital P by rho plus V into V square. See, sorry, V into V by 2. So totally it will be V square by 2 only after integration of V with respect to V. And dz can be converted into Z, capital Z. So this is very important equation, which is called as Bernoullis equation. Later, you can again divide by G value. Okay. So why we are dividing G, I'll tell you. We can divide it by G. Then we can get it as P by rho G. See here, P by rho G. V square by 2G. I'm dividing by G. Plus Z. Because G is divided by again G value. So it will be cancelled. So now we got the final equation where I can tell it as energy or the heads. So to name them, P by rho G can be said as potential, pressure energy or the pressure head, P by rho G at any given point of the flow. P by rho G, if you consider, that value is called as pressure head or the pressure energy. Then V square by 2G, if you consider, that will be kinetic head or the kinetic energy present in the fluid plus Z value. Z is the potential energy which is stored in the given head. Okay, so according to the given head, say for example 10 meters of height tank, if you consider, it is having some potential energy. And whenever you open some tap there, the water will easily flow from the high head to low head. So naturally, we have seen that how the liquids will flow from high head to low head depending upon the potential energy. That is Z. So for the inlet side and the outlet side for any given pipe, one can consider the inlet side I, outlet side O, or else you can consider inlet side as 1 and outlet side as 2. Any form you can consider. Then you can write it as, say for example, if I consider I and O for inlet and outlet, I can write it as Pi by rho G plus Vi square by 2G plus Zi for the inlet of the flow. It will be constant value. And this same value is also equal for any level of the water if you consider all the three heads. So we can equate it to equal. So any given point of the flow, say for example in home, if you are pumping the water from the sump, okay, from the ground floor to the first or second floor, if you are pumping the water at any given point of the pipe to that elevated tank or the high head tank where you are connected the pipe, between that total length, if you consider any point and if you find out what is the pressure, what is the velocity, what is the datum head, the total sum of these values will be same at any point. I hope the application is clear. So like that, inlet side or outlet side if you consider, or any in center point also if you consider, that I can write it as equal to other side. For other side, I told you I am going to consider outlet side. I'll write it as P0 by rho G or PO by rho G outlet side plus VO square by 2G plus Z0. So here I have considered right side the outlet side, left side as the inlet side. And this term, all of you please remember for all the numericals, P by rho G is the pressure head, V1 square by 2G is the velocity head, and Z1 is the datum head. So just note down this equation. This will give us total energy if you add all the terms. Any doubts in this equation? Bernoullis equation is the just integration of the Euler's equation, nothing else. But when the Bernoullis equation derivation is asked, you have to start with Euler's equation derivation. Once you get the Euler's equation, you have to convert it into Bernoullis equation after one step integration. Finally, we want to show that sum of pressure head, velocity head, and datum head, or pressure head, kinetic head, and the potential head is a constant. It remains constant throughout the flow. So this equation will be very helpful for many topics later in fluid dynamics. We are using this equation many times as our reference to find any energy or the head at any given points, or also if continuity equation is not known, or the in continuity equation we cannot substitute velocity acceleration to find the uh, discharge or area, we cannot find out. In such cases we can go by the energy also. So in such case we can find out one can find out the velocity if pressure or datum is known. Same velocity you can substitute in the continuity equation to find the discharge also. So one or the other way we can find out velocity by this equation, then we can also find out the discharge by the continuity equation. So like that, some other topics other than this subject of the chapter, this equation will be helpful to find the some other unknowns. Shall we proceed? All of you are following the equations. I think in Euler's equation there are no doubts, as we saw in the last class. Bernoullis equation is a just integration, one-step integration of the final Euler's equation. Okay. So next we will take some numericals to understand this importance of Bernoullis equation. So just write down. Yes. So in this first problem, they have given water is flowing through a pipe of diameter 5 centimeter under pressure of 29.43. See here, whenever we are talking about enclosed channels of the pipe channels, which are closed channels, there we are talking the pressure about the gauge pressures. So here they have mentioned as gauge pressure. If you want total pressure of the absolute pressure, you can add the gauge pressure with the atmospheric pressure. Then you will get the absolute pressure. And same problem if we have mentioned as water is flowing in a open channel or a just flowing, we assume that it is an open channel. I hope you are understanding. So for that condition, they have mentioned whether it is open or closed. They have mentioned it is a pipe. So means it is flowing in a enclosed channel of diameter 5 centimeter. So all of you assume a pipe of 5 centimeter diameter. In that water is flowing under the pressure of 29.43 Newton per centimeter square. Okay, that is gauge pressure, and with mean velocity 2 meter per second. So we can assume that it has velocity itself 2 meter per second it is flowing. Find the total energy per unit weight. Total energy per unit weight. Per unit weight we need to find out of water at a cross section which is 5 meters above. See here. Now this pipe, it is not exactly horizontal, or it is not kept at the ground zero. Where it is kept? When the pipe is at 5 meters above the datum line. So if you consider any line as 0 or our floor at 0 point, from that point it is kept at 5 meters, around 2 floors above it is kept, or 1.5 floor it is kept above. At that point we need to find out what is total energy per unit weight of this water. Okay, and you can take any cross section because cross section is same. The pipe is having diameter 5 centimeter. They have not mentioned any change of diameter here, so diameter will be remaining same. So pipe is kept 5 meters above from the ground, and in that water is flowing at a given pressure, and the diameter of the pipe is told, and velocity is also given. So now by just observing the problem itself, as per the Bernoullis equation, datum head is given 5 meters, velocity is mentioned in the problem, density is given for water, because water we should know for the standard, as a standard value, water density. G is also a standard value. Pressure is also given. Now, knowing pressure, velocity, datum, head, one can find out the total head also, or the total energy. So that's what they are asking, total energy. So by just converting some of the given diameter or some other units, okay. So here diameter is 5 centimeter. We can convert that into meters. That is 0.5 meters. Then converting this pressure why they are converting, because it is not in Newton per meter square, it is in Newton per centimeter square. So Newton per centimeter square, if you convert it into Newton per meter square, you can write it as 29.43 into 10 raised to 4 Newton per meter square. Then datum head is directly given in meters, 5 meters. So considering the Bernoullis equation to find the total energy, what is asked in the question. In the question they are asking this total energy. For this total energy, we know from the Bernoullis equation, that is given by P by rho g, V square by 2g plus Z. And that value we need to find out, that is called as total head for the one section of the pipe, because section of the pipe is not changing. So just substitute these values in this equation and find this answer. So please all of you use the calculator, substitute proper answers or the values and check the answer. Pressure is 29.43 into 10 raised to 4 Newton per meter square, divided by 1000 into 9.81, that is one term, plus velocity is 2 meter per second, so 2 square divided by 2 into 9.81, second term. Third term is the datum. So third term, datum is nothing but the elevation or the height at which the pipe is positioned, or the point at which the values are found out. So that point is 5 meters. Or you can consider the center of the pipe is at 5 meters. So that Z you can consider 5 meters. And once you take the sum of all these three terms, potential, kinetic and pressure heads, one can find out the total head or the total energy. So here total energy is around 35.204 meters. Please check the answer whether it is correct or wrong. Okay, 35.2038. Okay, correct. 35.2, 35.203. Okay, 35.2 is also okay. Okay, please keep this equation in mind. Next problem we can see. So this is just to understand what is the importance of Bernoullis equation. Now total energy present in the water at 5 meters height at this pressure is how much? 35.204. At this head the water is available. Once the tap is open, it will start falling. Okay, next we'll go to the other problem. Water is flowing through a tapering pipe. So tapering means a pipe is changing in cross section area. It is reducing. Like that, water is like a nozzle. Nozzle you can keep in mind. So water is flowing through a tapering pipe having diameter 300 mm and 150 mm. See here. Now I can assume at the entry the diameter of the pipe is 300 mm. After tapering for a given length, the diameter is reduced to 150 mm that they have given. So exactly it is half. So tapering is exactly half. Entry it is 300, outlet it is 150 mm diameter. And also they have mentioned also at section 1 and 2 respectively, so that you can consider. The Q is nothing but the discharge. The discharge through this pipe is 40 liters per second. So can anyone tell me how to convert this 40 liter per second into 40 meter cube per second? Okay, just comment in the chat box how to convert this 40 liters per second to 40 meter cube per second, because we need in SI unit. So that much is the discharge through the pipe. The section 1 is 10 meters above. So Z value is given. Z1 is given. Before tapering, the pipe was or pipe is on section 1 or inlet side is above ground by 10 meters from the datum. And section 2 after tapering 150 mm diameter, it is at how much? 6 meters above the datum. So by these dimensions, if you see 10 meters and 6 meters, 10 meters is above, 6 meters is below because of the less dimensions. So I can consider inlet side is at above position, outlet side is below, because it is 10 to 6 meters. There is a change in datum head. Find the pressure intensity. See now, in this problem, they are not asking the total energy, they are asking pressure intensity. Find the pressure intensity at section 2. If that at a section 1 is 400 kilonewton per meter square, so no problem. Pressure is given in SI unit at section 1, 400 kilonewton per meter square. Only change is what we need to find out pressure intensity at section 2 at the tapering end. That section we need to find out the pressure intensity. So then given the conversion, yes, 0.04 meter per second, very good. Divide it by 1000. Yes, later if you divide by 1000, it will be meter cube. So please keep in mind how to convert that liters into meter cube. So coming to the sketch for reference, if you want to draw the sketch, you can draw like this. Now after reading all these given data, we understood the 300 mm diameter is above the ground 10 meters. Another section of the pipe, tapered pipe, 150 mm diameter, it is at 6 meters. So taking this all given data, okay, one can go for the finding unknown terms. Now if you just recall the Bernoullis equation, we cannot directly find out the pressure. Why? Because in the pressure equation, if you see here in this pressure equation, pressure of one of the section is given, that is 400 kilonewton per meter square, where it is a section 1. So section 1 is given. Velocity they have not mentioned anywhere. Datum it is mentioned, 10 meters and 6 meters they have mentioned, but velocity nowhere it is mentioned. Now to relate this velocity or acceleration, what they have mentioned is the discharge. Are you understanding? So now to find out one of the unknown pressure, even both the velocities are also not given, you can go by discharge or the continuity equation. So how to find out the discharge? Discharge is Q equal to A into B. Either you go by A1 V1 section at 1, or I can go by at section 2, I can go by A2 into V2. It will remain same. Discharge will remain same for any type of cross section in the given same flow. So I can find out velocity by the continuity equation. Then I will substitute in this equation to find one of the pressure. So see here. So I'll go by discharge equation. Discharge is 0.04 meter cube per second. Okay. I can write it as A1 V1 equal to 0.04. I hope you are understanding. Or even at A2 V2 also I can write it as 0.04 meter cube per second. Both multiplication, if you see, will be equal to Q, 0.04 meter cube per second. Now in these equations, area is indirectly given. How it is given indirectly? Diameter is mentioned here. A2 is mentioned with diameter 2 as 150 mm. Since they have mentioned in the problem itself, it is a pipe. So I'll assume that pipe is a circular pipe. Okay. So pipe is a circular. What I will do now, I will find out the area. So area 1 and area 2 can find out by pi by 4 d square. So pi by 4 d1 square you can find out. Pi by 4 d2 square you can find out. That will give us the area. So please check area 1. At area 1, the value is around 0.0701 meter square. Then section 2 area is 0.01767 meter square. So using these two A1 and A2 area values, now one can find out velocity 1 and 2. Once you find out velocity, just we need to substitute in the Bernoullis equation for section 1 and 2. So please check these velocities. V1 is equal to 0.04 by A1. A1 is 0.0707. Then for velocity 2 at section 2, velocity is 0.04 divided by 0.01767. So please keep in mind, velocity area may be changing, but not the discharge. Discharge is going to remain constant. That we have seen in the continuity equation or the conservation of mass also. Whatever is entering at the inlet side, same will be at the outlet side. 'Once you are done with finding velocity v1 and v2 at section 1 and 2, please inform. 0.07069. 069. Okay. So that value is okay. Area 2 and velocities. These others also find out the values. Others all are attempting because only few are replying. V1.5657. 5657. Okay, no problem. See later if any results are wrong, later after IA you don't claim that same problem is solved in the class and it was the answer is like this. You need to cross check. Once all of you can cross check the values with my notes or any problem in the books. If it is wrong, don't worry. You keep it what the actual results you are getting as per the given formulas. Finally, that only is considered as correct. not for as per the book or as per the result what I have written in the notes. Once you are able to prove the formulas with results, that is more than enough. Other values are correct. This velocity at section 2 and area at 2. If they are correct, we will find the pressure. Pressure at section 2. So for that, we again recall the equation of Bernoullis for two sections. So here two sections are changing with the diameter. So we have considered P1 by rho g plus P1 square by 2g plus Z1 equal to outlet side or other side P2 by rho g plus V2 square by 2g plus Z2 that we can consider to find P2, because in this equation now after finding V1 V2 we left with only P2. So P2 is coming around, just read the result here. P2 is around 436.8 kilonewton per meter square. 436.8 kilonewton per meter square. So this pressure is very high because the pipe is tapering, it is acting like a nozzle, okay, and also it is flowing from high head to low head. So this potential energy plus tapering of the or the change of cross section area, velocity is increasing, okay, and also the area is also reducing. So due to this, what is happening? There is a lot of change of pressure. There is a lot of increase in the pressure of the outlet side. That is around 436.8 kilonewton per meter square. V2 is 2.265. Okay, 2.265. Yes, if you want to keep that answer itself, you keep that only. And please confirm this result. So once you are able to find out or substitute these results in calculator and find the results, it is more than enough. You can solve many type of problems. The next problem will say just to understand what is the difference from earlier problem. We will not go in deep. We will understand what is the difference between the earlier problem and the latest problem. Just one of you find this result P2. How much you will be eating? Pressure at section 2. We'll go to next problem. Yes, answer 436.83. 436.83. Okay, kilonewton per meter square. Okay, next problem we'll take it now. So we'll see the question and we'll take it in next class. Okay, and please wait in the break time also. I'll explain one more problem in the viscosity concept, which is asked by one of the students. Okay, next problem in this Bernoullis equation is a non-uniform part of the pipe. Non-uniform part of the pipe. Now again, assume may be tapering or it may be changing the cross section. Pipeline 5 meters along is length. So length is 5 meters long. It is not the diameter of the datum head. 5 meters the pipe is long. Is laid at a slope of 2 in 5. Now we'll see how to convert this slope 2 in 5. Okay, it is laid like that. It is having the slope of 2 in 5. Two pressure gauges, each fitted at upper and lower ends. So we don't know which is upper or which is lower ends. Reads 20 Newton per centimeter square. What is that 20 Newton per centimeter square? It is at the upper side. Lower end reads 12.5 Newton per centimeter square. Okay. Next sentence is if diameter at the upper end, if the diameter at the upper end and lower end are 15 centimeter and 10 centimeter. So as per the given diameters here, upper diameter is 15 centimeter, lower diameter is 10 centimeter. So means lower side the diameter is reducing. Okay, and but the pressures are different. Pressures are 20 Newton per centimeter square. Lower side the pressure is 12.5 Newton per centimeter square. And the slope is 2 in 5. Length of the pipe is 5 meters long. So depending upon this 5 meters and 2 in 5, we need to find out how the datum point is changing. And one more point you can just note down here. In any of the sentence, they have not mentioned anything about velocity of the flow, and they have not mentioned about the datum head itself. Anywhere they have not mentioned where the pipe is positioned, at what height, they have not mentioned. So in such cases, we have to consider one end of the pipe at 0 point, datum 0. Is that clear? So in the sketch you can see whatever the lower point is there, the streamline or the flow line, if you see the flow line, the lower side point we have to consider 0 now because datum point is not given anywhere. And this height, the outlet side or the D1 side, if you see whatever the height is there, this we need to find out by using the slope and length of the pipe. Okay, so using the slope, one can find out now the Z1 value. Z2 we can take 0. So that we can do whenever the datum point is not given in the problem. So one of the point we have to consider 0. So now go by diameters are given, you can find out areas. P1, P2 is also given. Okay, P1, P2 values are given as per the sketch. Then what else is given? Diameters are given, P1, P2 are given. Slope and height is given. Now to convert that slope into height, what we are doing is this 5 meter length, we are multiplying it 2 by 5. If you take, we will get what is the height from this point to the ground point. So this problem will continue after break. Okay. Until the break time completes, I will solve one more problem on the viscosity. So those who are interested, you can attend that break part. In that break, I will solve one more problem on the viscosity. And this problem we'll consider in the after the break. Okay, that viscosity problem is I've taken here. The question asked is the question is like this: if the velocity profile of a fluid over a plate is a parabolic, profile of the velocity above the plate. So one plate is kept on the table. Okay, on that the fluid is flowing, and the profile of that velocity how it is changing? It is changing with respect to parabolic shape. So that parabolic shape you can recall from the concept what you learned in the Newton's law of viscosity here. Yes, here you can just observe the parabolic shape. Yes, here. There may be different conditions also. See the profile of the velocity. Here they have mentioned non-linear, that is parabolic in shape. They are not given the equation. So that equation we need to assume. One more type may be linear. It may be changing linear with respect to some fluids. Some fluids may behave like circular profile, parabolic profile, hyperbolic profile, depends. So like that, the profile of the velocity is given in the problem. So that profile you understood, that is the parabolic shape with vertex at 20 centimeters. So the point at which the parabolic shape is ending, or the vertex of that parabola is 20 centimeter. So that 20 centimeter we are considering at this point, at the tip of the curve, or at the point of view where it is shown, that line from the plate, the height we are considering 20 centimeter, 20 centimeter from the plate, where the velocity is maximum, that is 120 centimeter per second. Now here, if you see, it is shown only for the between these two plates. If you take a pipe, in a pipe, what will happen? The velocity will be maximum at the center point, and again, if you continue this profile to the other end of the pipe, okay, other radius of the pipe, it will again follow the same profile. So it will be maximum at the center. It will be zero at the surface of the pipe or the inner surface of the pipe. So like that, at 20 centimeter from the height of the plate, the velocity is 120 centimeter per second. Calculate the velocity gradients. Here they are not asking velocity, they are asking velocity gradient and shear stresses. So velocity gradient is from the Newton's viscosity law. We know that shear stress tau is mu into du by dy. So I hope all can remember that equation and recall now for this problem. Tau is equal to mu into du by dy. Mu is the coefficient of viscosity. Du by dy is the velocity gradient. That we need to find du by dy values. And after finding velocity gradients, we need to find out shear stresses, that is tau, that is the formula. At a distance of 0, 0 means on the plate. When the liquid is in contact with the plate, at that distance it is 0. At that distance, what is velocity gradient du by dy and shear stress tau. And also we need to find out tan at 20 centimeter from the plate. If the viscosity of the fluid, so viscosity of the fluid is given 8.5 poise. So unit you can just focus 8.5 poise is given. Now can anyone reply me how to convert this poise into our SI units, and what is that SI unit? In which SI unit we need to convert, and what will be the value? And later also we'll consider for the linear variation. If the variation of the velocity is not parabolic, if it is linear, then how to solve? Now we'll just concentrate on the parabolic profile. So one of you just convert that 8.5 twice to the SI unit. .85 units, viscosity units. That's very good. 0.85 Newton second per meter square. So that you can take it for substituting the SI unit values. Yes, 0.85 Newton second per meter square. So that value you have taken in SI unit 0.85 Newton second per meter square. And in the problem also they have taken given velocity is 120 centimeter per second. So this centimeter also we are converting into meters. So that will be 1.2 meter per second. Distance they have given 20 centimeter. We have taken 0.2 meters. So I will explain you how to solve for the parabolic shape. You can focus on the linear shape also later. So in both conditions, the velocity at the top at the given position of 0.2 meters, it is 1.2 meter per second, and velocity in linear also, the height and velocity are going to consider same, but the profile is different. So depending upon this change in the profile, how the velocity is going to change, or how the velocity gradient is going to change, that we can discuss in the linear condition. So parabolic condition will focus now. I hope this type of question is not asked many times. So I think I have skipped in this discussion. As one of the students has asked this type, I consider this also as one of the important question also. Okay. So now coming to the Newton's law of viscosity, I have told you, you can use this equation. Now coming to the parabolic profile, the generalized equation what you can consider is velocity as, or the equation of parabola in this profile, which can be taken as parallel to plate to consider. That can be written as a into y square. A is a constant. A, B, C are the constants here. You can write it as a y square plus by plus c. Or in many cases, the equation will be given in the problem itself. How the velocity is going to change. The equation will be given. According to that, we need to find out the constants, and later we can find out the velocity gradient and the shear stress. So all of you can note down this generalized equation for the parabola. U equal to ay square plus by plus c. If it is a linear, I can take by plus c. These two will be constant, b and c will be constant. I can consider for a straight line or a linear variation like this. For this linear variation, straight line, at an angle, it is shown. That line I can consider it as by plus c. So for parabola, we'll consider ay square plus by plus c. Now, going for the next step, now parabolic equation we taken for a general case. So here we'll put all the conditions what is given in the problem. So for finding constants ABC, the parabolic equation, first condition what they have given, at distance 0, that is y is 0, velocity will be 0. This everyone knows from the Newton's law of viscosity. When the distance is 0, velocity will be 0. If you put these two values in the equation of parabola, here, here, u is 0, y is 0. So what will happen? C equal to 0, constant will be 0. So we found out constant as 0. The C value is 0 from the first condition, that is when y is 0 and u is 0. So once this C value is known as 0, means it is not important for our problem. So C will be 0. Second condition is we need to find out the velocity at 10 centimeter. Second case, that is at 0.1 meters. At 0.1 meters, if you see, velocity is unknown. That we need to find out. Velocity is not at all given. But in the third case, if you see, at a distance of 20 centimeter or zero point 0.2 meters, velocity is given in the problem itself. It is 1.2 meter per second. Now, for velocity gradient also, I can consider du by dy. Now, from the concept, the velocity gradient will be 0 at the top position. At this position, there is no velocity gradient will be available. Or even if you take the pipe also, in the pipe, the parabola will be coming up to vertex. Now again from vertex, it will be going back, and again it is joining up to the inner surface of the pipe and the top surface. If you take complete diameter of the pipe, this parabola will be completed. Now where the velocity is maximum, velocity gradient will be 0 there, because there is no change in the velocity with respect to distance y, because that is the maximum distance at which, or the center of the pipe at which maximum velocity is already possible. So there will be no velocity gradient. That is concept. So from that we are going to consider, because if you see velocity gradient at the bottom, here it will be very high. At this point. How it is high, we'll see from the problem. Here it will be having some value. Here it will be not having any value. Where the maximum velocity is reached, velocity gradient will be 0. So that you can consider at that point, third condition, at maximum distance 0.2 meters and maximum velocity 1.2 meter per second at the vertex of the parabola, because in the problem itself we have mentioned it's a vertex. It's the vertex of the parabola 20 centimeters. Means that's the maximum point of velocity. So that point we have to consider du by dy as 0. Please note down this point. This is very important for considering the velocity gradient as 0. Even by steps also we can prove that du by dy is 0. The next is using above conditions and substituting the parabolic equation. So as I told you, if you differentiate the parabolic equation du by dy, what I'll get? I'll get the velocity gradient du by dy. If I differentiate with respect to y itself, this is called as velocity gradient. This only we need to find out for all the three positions. So once you take the differentiation, I can write it as 2ay plus b. To differentiate this equation, I can write it as du by dy 2ay plus b. Correct? So once you found out this value, you can substitute for the given conditions. So now du by dy equal to 2ay plus b is there. Now known values are at velocity 0 and velocity at 1.2. That value you know. So what I'll do now, du by dy, I'll put 0 here for the condition C. You know that at condition C, velocity gradient is 0. That can be written as 2a into y is what? At top position, the distance is 0.2 meters. I'll substitute here 2a into 0.2 plus b. B is not 1. Constant we don't know AB. But C we found out that from the first condition at 0. So C we have not considered. And in du by dy, C is also not there. So we can write it as 0.4a plus b equal to 0. With this equation, du by dy equation. That is the first condition. Or I can call it as equation number 1. One more is, you can take the same equation without derivation. Equality will be same. If you derive or integrate, not integrate, whatever, if you consider with the equality sign, the same equation should give the same result also. So to consider two equations and to find the functions AB, what I am doing is, I am again considering the parabolic equation itself. U equal to ay square plus by plus c. So in this equation, if you substitute, because in the third condition, here velocity value is also given. But in the other conditions, we don't know. Velocity in the second condition, we don't know. We cannot take the equation. So that's why in the third condition itself, we are taking with du by dy without derivation. Both conditions we are taking and we are naming it as one and two equations. So here I'll name this equation at the third position 1.2 equal to 0.04a plus 0.2b as second equation. Now by calculator or by solving these two equations, one can find out a as minus 30, b as 12. So please one of can try with the calculator to solve these two equations to find the two unknowns. You can find out a as minus 30, b as 12. Please check the constant AB, how much you are getting by these equations. Are you getting minus 30 and 12? Equations are 0.4a plus b equal to 0, 0.04a plus 0.2b equal to 1.2. These are the two equations. And once you solve these two equations, a is minus 30, b is 12. I think you can solve this. Once you get that 30 and 12 for AB values, that you can substitute in either parabolic equation or the derivative of that parabolic equation for the velocity gradient. Once you substitute that in equation of velocity of parabolic profile, here a is minus 30 into y square, y is also given at the third condition, b is 12, c is 0. So without applying the conditions, now I can write it as minus 30 y square plus 12y equal to u. If you take the derivative with respect to y, or if I write the velocity gradient as du by dy, I can write it as minus 60 into y because it is minus 30 into 2y. 2 into 30 will be 60. So that will be equation converted into minus 60y plus 12. All of you are understanding the steps. Those who are not taken the break have understood the steps. The parabolic equation we need to assume here because it is not given in the problem. So generalized parabolic equation we have assumed. Then you have to take the differentiation. So once you take the differentiation, it will be velocity gradient. Yes. So coming back to this problem, now you can see these are the two equations. If you want to find velocity, you go by this equation at any y distance. You put the value. Say for example 10 centimeter if you want the velocity, you put 0.1 square, here 0.1. You can find the velocity for that given parabola. So please check one of you velocity at 0.1. How much it will be in the parabolic condition. Then same du by dy because in the problem they are not asking velocity. You can also find out. You just check the change of velocity with parabolic nature. But in the question they are asking velocity gradients. So velocity gradients at plate, that is y equal to 0 if I take. Velocity gradient is how much? Minus 60 into 0, 0 plus 12. It will be 12 per second. So this will be the highest velocity gradient what is possible, or the variation of velocity which is possible at the plate. There more shear will be taking place. Next is at point 1 or the 10 centimeter if you take minus 60 into point 1 plus 12. So that will be coming around 6 per second. Why it is 6 per second? Because units are velocity is meter per second divided by meter. So we left with per second. Then velocity gradient at the tip or the top distance, that is 20 centimeter or 0.2 meters if you consider, minus 60 into 0.2 plus 12. So that will be minus 12 plus 12. It will be 0 per second. At the tip, there is no velocity gradient which is present at the tip, but there will be high velocity which is possible. Now the same value you consider for finding directly this shear stress. So shear stress finding, all of you know earlier, just substitute the given viscosity value 0.85 du by dy for all three conditions. You can substitute the values and you can find out the shear stress. So shear stress is maximum at the plate and the liquid interface, that is 10.2 Newton per meter square. At 0.1 meter, the shear stress is 5 Newton per meter square. See, it is not exactly half because it is a parabolic profile. If it is a linear profile or some other profile, it may be half. Here it may be half. And at tip position, there is no shear stress because velocity is maximum, there is no resistance. There is no maximum resistance which is applied on the liquid. So shear stress will be 0 at the tip at 20 centimeters, where the velocity is maximum. So I think this finding shear stress will be simple for you. But up to coming to du by dy is some other steps are required. That's how much is the velocity at this point. At point 1, tell me the velocity. Velocity at plate 0, velocity at 1.2 distance, or sorry, 0.2 meters. Velocity is how much? 120 they have given. Or you can substitute the value and find the velocity, whether it is correct or not as per the equation. So for point 1, if you find the velocity, what I have written here unknown, that velocity you can find out by this equation. No answer? Or the student who has asked the doubt can answer here. I'll briefly repeat the steps here. In the question, they have given the velocity parabolic profile, and at the vertex, at the tip of the parabolic or the center of the parabolic, they have given maximum velocity 120 centimeter per second at a distance of 20. What we need to find out is velocity gradient, du by dy we need to find out, and shear stress we need to find out at these 3 points, 10, 20, 30, 0, 10, 20 centimeters, with viscosity value 8.5 pies or 0.85 Newton second per meter square. Okay, so to find this, in the problem, they have not mentioned any equation for the parabola. If they are not mentioned, you can go by generalized form. If they have mentioned, take that equation, take the differentiation, du by dy, you take the differentiation of the velocity, and you can find the velocity gradients. So for that generalized case, I have taken this equation, u equal to ay square plus by plus c, generalized equation for the parabola. And here I have taken y and du by dy, both equations, by considering all these three conditions. If you consider first condition, y equal to 0, velocity will be 0. So by that, constant c will be 0. So c will be 0 for all the cases. Now, to find AB constants, second case we cannot consider because velocity is not given, only distance is there. But for the third condition, we know the velocity as well as distance y. So this equation, parabolic equation, we can consider for the third case, substituting y and u both. And in that third condition, at the tip or the center of the pipe, if you see, the velocity gradient will be 0. This is a principle. So by that principle, du by dy, we can consider it as 0 at 0.2 meters. So taking those two equations without differentiation and with the differentiation, that is du by dy and u of the parabolic equation. Later, you can substitute the conditions by knowing a and b constants. So once you solve these two equations with differentiation, without differentiation, and if you know the AB values, one can find out either all three velocities or all three velocity gradients. And same can be continued for the linear case. The linear case, we can take the straight line equation, generalized straight line equation, ay plus b, with differentiation it will be a. So by these two conditions, you can substitute the values and find AB values. So later you can proceed with the steps. Have you understood or no this problem? Okay. I will continue with our Bernoullis equation. So the student who has asked this doubt or this problem, I think he is not present in the class or he is not replying. This is the problem with the online classes. Okay, going to the next problem. So as I mentioned in the third problem of this Bernoullis equation or the concept of Bernoullis equation. So question comes how to remember that this problem can be solved by Bernoullis equation only, because here they have mentioned the pressure points, they have mentioned the length and tapering of the pipe, and what they are asking is here. Also diameter is also given. They are asking determine quantity of water flow. So one can assume we can solve it by continuity equation. Yes, we can solve it by continuity equation because we know the area. But how to find the velocity? Now to find that velocity for continuity equation, we have to go by Bernoullis equation. That is the interrelation between this continuity equation and Bernoullis equation. So you find out area by knowing the velocity, sorry, diameters, pressure values are given. Okay. Now this is very important step. Slope is given 2 in 5 and the length, center length of the pipe is given 5 meters. Z1, sorry, Z2 as per this case, Z2 I can consider it as 0, taken 0. Z1 I can consider it as depending upon the slope. Now how to consider that? We can take Z1 as 2 in 5 for 5 meters. So for 5 meters distance, slope is 2 by 5. Today, the Z1 height will be 2 meters. This vertical height from Z1 center point to the center of first point. If you take the vertical distance, this distance I'm talking, this distance will be 2 meters. So that they have written 2 by 5 into 5, 2 meters. Is the Z2 value, sorry, Z1 value. Z2 will be 0. Okay. Now, as they're asking the discharge, so again he is trying to find out by discharge Q equal to A1 V1 and A2 E2. So either by any one equation you can find out discharge. So A1 V1, V1 is 1. A2 V2, V2 is 1. What they have done? They have equated A1 V1 equal to A2 V2. A1 V1, A1 A2 is known. V1 V2 is not known. So what they have done? They have kept as it is. Because we cannot solve the next step. Because V1 is also not known, V2 is also not known. Just they have taken the ratio of this A1 and A2. So they have written V1 equal to 0.444 V2. That is A2 by A1 ratio is 0.444. Now they required to relate some equation which is containing V1 and V2. Which equation is relating V1 V2? That is the Bernoulli equation at the entry and outlet side. So in the pipe given, taper pipe, inlet side, outlet side velocity we can relate also by Bernoulli equation. That is pressure head, velocity head, and taper head. So consider that P1 by rho g, P1 what they have considered 20 into 10 raised to 4 Newton per meter square. 20 into 10 raised to 4 Newton per meter square is given. P2 they have considered 12.5 into 10 raised to 4 Newton per meter square. So take those values here in this equation. V1, V2 is not known. But what we can do here is V1 we can write it as 0.444 V2 so that both sides will become V1. Or else you substitute V2 as V2 equal to V1 by 0.444. That also can be done. Keep any one velocity. Z1 is 2 meters, Z2 is 0 meters. So by this one can find out velocity 1 or velocity 2. Any one value we can find out. So as V1 is substituted as 0.0444 V2, one can find out V2 value. So V2 will be coming around 15.35 meter per second. Once you know any one velocity, you can find out distance. The problem is over. So please note down the steps. So please make sure that if you have any doubts and asking, and also please attend to the class also, or at least attend that the class for clearing that doubt what you ask. All of you understood this finding velocity and discharge. Just to find velocity, they went for Bernoullis equation. Just to find the velocity. Then once the velocity at entry or outlet is known, discharge can be found. Because the rest all values are given in the problem itself. So discharge by V2, or even if I go by A1 V1, you can find out discharge 0.1205 meter cube per second. Please check the answers in calculator. The problem is understood to all. The question may be, when V1, V2 both are unknown, then how to find out these values? So for that, what they have done, from the continuity equation, they have equated A1, V1, A2, V2, and they have kept either V2 in terms of V1 or can keep V1 in terms of V2. And in this Bernoullis equation, either you can write V1 as V2 terms or can write V2 as V1 by 0.4. Then you can substitute to find one. Yes.
Excuse me, sir.
Yes.
Sir, can you find it by A1 and V1 discharge?
A1 and V1, yes. So
Sir,
A1
why
value,
V2?
why?
V1 value is given.
V1 value is given.
So A1 is given.
A1 is given. A2 also is given.
Yes.
You can go by A1, V1 also. So V1 where it is? Yes, here you can find out V1. Just find out V1. 0.444 into 15.35. You find out V1.
Okay, sir.
You can find out V1. Take area 1. Area 1 is how much? By diameter 1. Diameter 1 is 15 centimeter. Area 1 is 0.01767. Area 1 into V1. V1 is here. You can take V1 from here and find the discharge. Whether it is coming same or not, you check me. Tell me the answer. That will be same. A1 V1 or A2 V2. Find the discharge. Okay, now A1 is also visible. V2 is also visible. V1 equation is also visible. You can find out A1 V1, or you can find out A2 into V2 and find both the results. Both should be same. Is it 0.1205 meter cube per second?
Yes,
15
sir.
point,
Correct.
correct? Okay. 15.35 into 0.444 will give us V1 into A1 0.01767. You may get 0.1205 meter cube per second. Okay. So next you write down one of the important equation. If the Bernoullis equation is considered for the real fluids, so whenever you call the real fluids, first important factor is the viscosity or the viscous losses and the friction losses. So to consider these extra losses which are present, because until now if you see the Bernoullis equation, in any pipe flow we have not considered viscosity or the friction. All these three problems we didn't consider any friction or the viscosity losses or the viscosity property also or the value. But in reality, these terms will be coming into picture. Okay, so for that, the combined losses, what they have written is HL. You can consider this head loss or loss of head due to viscosity or the friction losses. So that same Bernoullis equation, what they have done is at the entry side, the total energy.
Sir, your voice is taking.
Okay. Now it is clear. Okay. So to consider the extra losses in the real fluids, in Bernoullis equation, what they have done is they have added this extra loss HL or the loss of head due to viscous forces and the friction forces. You can note down this equation, that is P1 rho g plus V1 square by 2g plus rho at the entry side, and after outlet side these losses should be added, because once the fluid start entering, at that point only we don't have any viscosity or friction losses of the pipe. But when it is leaving from the pipe, like at the section 2, this should be P2. To the right side, we change this equation, P2 by rho g plus V2 square by 2g plus Z2. This outlet flow, whatever is there, may not be equal to inlet flow or the sum of these all heads. It may not be equal in the real fluids I'm talking. So in the real fluids, with viscosity and friction losses if you consider, then those losses you have to add at the outlet side, because once the fluid enters and come at the outlet side there will be extra losses because of the friction of the pipe and liquid, or there will be resistance of the liquids between the layers. Okay, so those losses we need to consider at the HL. Or sometimes they find out all these sum of these two heads, total head at 1, total head at 2. The difference of these two heads also can be found out as HL. Okay, one other side. So effective head you can write it as H1 minus H2, where H1 is left hand side equation, H2 is the right hand side equation, only up to Z2. So to consider this, we'll take one problem. in this, a pump has a tapering pipe running full of water. Pump has a tapering pipe running full of water. The pipe is placed vertically. Pipe is placed vertically with the diameter at the base and the base and the top being 1.2 meters and zero point 0.6 meters respectively. So here base diameter and the top diameters are given. Base diameter is larger, 1.2 meters larger diameter, and the top diameter is 0.6 meters respectively. The pressure at the upper end is 240 mm of Hg. Now see here, pressure they have not given by gauge pressure or the FP pressure. They are mentioning the pressure in mm of Hg. Okay, mm of Hg, vacuum pressure. So you can recall the concept of this vacuum pressure in mm of Hg. Later we need to convert this into absolute or the gauge pressure. And whenever this vacuum term comes, we need to take it in negative because vacuum is below the absolute zero. So whenever the pressure is below absolute zero, that pressure we are calling it as vacuum pressure, and such pressures we can consider it as negative pressure. That is 240 mm of Hg mercury. Please recall to convert this mercury head into water head or whatever, or if you are asking the result in mercury flow itself, you can keep it as it is. Next, why the pressure at the lower end means at the larger base, 1.2 meters, that point, lower end is 15 kilonewton per meter square. So here no issue, they are given in the SI unit. I think 15 kilonewton per meter square at the lower end may be a positive pressure. Assume the head loss to be 20% of the difference of velocity head. See, this question is very important. This covers almost all the equations of this chapter until what we have studied. Those all equations are covered in this problem. Why? Because here pressure at the head loss is also given HL for the real fluid, considering as a real fluid. They have given, assume the head loss to be 20%, means 0.2 into difference of velocity heads. That is v1 square by 2g minus v2 square by 2g. If you take the difference of velocity heads into 0.2, that is 20% if you multiply, that will be the HL value. Last sentence is calculate discharge. Q we need to find out, so we need A1 V1 or A2 V2. The flow is vertically upwards. Flow is vertically upwards, and difference of elevation is 3.9 meters. Means the height of pipe is 9 meters, or Z2 value is 3.9 meters. The sketch is shown. So note down the sketch and equations. Just 1 minute, I will take the break. I'll come back. So in the problem, the sketch is drawn like this. Inlet side, they have told diameter is 1.2 meters. Diameter at the outlet side of the upper side, it is 0.6 meters. Z1 0, Z2 is itself is the height now. So Z1 and Z2 difference, if you see, it is not a inclined pipe or it is not a horizontal pipe. It is a vertical pipe. So in that, height of the pipe itself becomes the value of Z2. Z2 is around 3.9 meters. It is given in the problem. Elevation or the vertical height is 3.9 meters. Pressure at 1 is given 15, or the diameter at larger diameter pressure is high, 15 kilonewton per centimeter square. Pressure at the outlet side, problem they are mentioning vacuum or whatever, we will take consider that same pressure. So it is vacuum pressure. So due to vacuum pressure, P2 you can observe here. P2 by rho g, pressure head. Here, what is given? Pressure at the upper end is 240 mm of Hg, vacuum pressure. Okay, so P2 by rho g, you can consider pressure head, or the problem itself you can note down the pressure head at the upper end is 240 mm of Hg. Pressure head 240 mm of Hg, vacuum. So to consider that vacuum, we can consider negative sign, minus 0.24 meters of Hg into density of mercury. All of you know 13,600 density of mercury. G is 9.81. So now I can convert this mm of Hg into Newton per meter square. So this value is around minus 32,019.8 Newton per meter square after converting from the mm of Hg to gauge pressure Newton per meter square. Then is the question they are asking discharge. As we discussed earlier, you can take A1 V1 A2 V2 equation, keep it ready. Okay, or to find that you can keep the values in one of the velocity. So they have kept here 4 into V1 is equal to V2, or can write it as V1 equal to V2 by 4. Both are same. So as the diameters are given, they have taken diameters.
Excuse me, sir.
Yes.
So why negative sign?
Vacuum pressure. Vacuum will be below 0. So below 0 value means it is negative.
Okay.
Here, vacuum pressure. In the problem, if they have not mentioned vacuum, then this will be a positive pressure, above absolute pressure. Is it okay?
Yes, sir.
So keep in mind, absolute pressure, if any value is given directly without any sign, you can take it positive, gauge pressure or the atmospheric pressure or any pressure. Or if they tell absolute pressure also, it can consider it as positive. All the values will be positive. But whenever they tell vacuum pressure, then it will be below absolute 0 point. So absolute 0 point, if it is below, then we can take this sign, minus sign. We need to consider for the vacuum because it will be below 0. Below 0 pressure, whatever is there, that will be negative sign. So we have considered minus 32,019.8 Newton per meter square. So concept of A1 V1 equal to A2 V2, you know, either you can take by A1 by A2, you can take the ratio, or you can take D1 by D2 ratio, both are same. You can keep as it is, but D1 by D2, if you consider, you could take square because it is pi by 4 D square. So as they have told pi, the area of the pipe will be pi by 4 D square. So D square will be remaining here. D1 by D2 square will be remaining. Pi by 4 will be cancelled. So from that, I can write V2 as 4 into V1, okay, as per the given areas of the diameters, or I can write V1 as V2 by 4. So one of you check the diameters. Are they 4 times? I think we have considered by area, sorry, diameter squares. If they consider, we will get 4 into V1 equal to V2. It is 2 times. Diameters are 2 times. Because of square, it will be 4 times. 4 V1 equal to V2. So in the Bernoullis equation, considering with loss, why? In the problem they have mentioned the loss of the head here. Assume the head loss due to or head loss is 20% of the velocity head difference. They have not mentioned the value, but they have given indirectly. Okay, 20% of the velocity head difference, that will take later. But this head loss we need to consider. So in the Bernoullis equation, assuming the real fluid is flowing, we have considered HL. So difference of height or datum, Z2 minus Z1, as I told, it is 3.9 meters. Height of the pipe itself is 3.9 meters. So Z2 minus Z1 is known. Then velocity head difference. Okay, velocity head difference, if you see, V2 square by 2g minus V1 square by 2g. If you take into 20%, the 20% is 0.2. Just a minute. So this difference is taken to multiply with 20%, 0.2, so that we can find out HL value. But here we don't know V2 as well as V1. So this we can find out by the other forms. So I hope this HL, how we have considered, is understood. Difference of velocity head difference into 0.2, that will give us HL. So now can you tell me by this HL, if you substitute with this equation and Z1, Z2 difference is given, okay, P1, P2 is also given. P1 is 15 kilonewton per centimeter square. P2 is just we have found out minus 32,019.8 Newton per meter square. So all these values are given. Now we left with V1, V2 in terms of V1 and V2. So all of you substitute the values. P1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g plus, now I will try to keep in one form, that is in V1 form. So V2 will be how much? V2 is V1 by 4. I'll write V1 by 4 here. V1 by 4 square by 2g plus Z2 plus HL is, I can write it as 0.2 into V2. What is V2? We have considered V1, V2 is 4 V1. Okay. Just a minute. V2 can be written as V1 into 4. Yes. V2 you can write it as V1 into 4. Okay, here minus V1 square as it is divided by 2g. So this entire equation you have to consider with the given parameters as per the given parameters in the question. I can write HL in terms of V2 and V1. V2 I can write it in terms of V1 as 4V1, and one can find out the unknown value of V1. So once you know the V1 value, later by discharge equation we can find out V2 also. So once you check this velocity 1 or velocity 2, we'll stop the class. Here velocity 1 is coming around 0.9865 meter per second. As per that V1, discharge is around 1.1157 meter cube per second. So keep the Bernoullis equation and head loss in terms of V1. Wherever V2 is there, you can keep V1, or other way is also correct. You can keep all the terms in V2 also. V1 I can write it as V2 by 4 also. That also can write. But keep all the velocity terms and head loss terms in one of the velocity term, so that you can find out either V2 or V1. If you find out V1, it is around 0.9865 meter per second, so that we can find out discharge. The steps are clear. So using the same steps, you find out velocity 1 and 2. Then using either A1 V1 or A2 V2, you can find out the discharge also. So how much is the quantity of liquid coming out of this pipe? So which fluid is flowing in the pipe? Water is flowing. So how much water is flowing out of the pipe or entering to the pipe is 1.1157 meter cube per second. This much volume of water is flowing per second through that pipe. Okay, we'll stop the class here. Next class, we'll take the flow measuring devices. This completes the Bernoullis equation and application of the Bernoullis equation. Next class, we'll take the flow measuring devices in open channel and the closed channel. Okay, thank you.